a very important fact, and this will come up again in a little bit. So every elementary matrix is always invertible. So first of all, every elementary matrix is always square. So that means we can possibly talk about invertibility. But indeed, all of these operations, these elementary row operations, can be reversed. So that's why it's invertible. If you can do an action and then undo it and wind up back where you started, that means that action is invertible. So, for example, what was the matrix E1? We got that by interchanging rows 1 and 3 of the identity matrix. Well, how do you undo that? If I interchange rows 1 and 3 again, I will get back to where I started. So this thing was interchanging rows 1 and 3 on the identity matrix. If I do it again, that gets me back to the identity matrix. So interchanging the inverse of this row operation is the same exact row operation. If I interchange rows I and j once and then do it again, I get back to where I started. So that's why this thing has itself as an inverse. If you apply the action twice, you get back to where you started. And then remember, this is the thing where we multiplied the second row by a non-zero scalar. So multiplying any row by a non-zero scalar can be undone, right? So if I multiply the non-zero scalar 1/2, how do I undo that? Well, then I multiply by the how do I get this thing back to the identity? Multiply the second row by the non-zero scalar 2. So that's, what's the inverse of this elementary operation? It's going to be this elementary operation. So take the identity matrix and multiply the second row by 2. If I multiply this thing by this thing, I'll get back to the identity matrix again. So the inverse operation of replace row I with C times row I is replace row I with 1 over C times row I. And again, C is not 0, so this is legitimate. And then finally, this was the elementary operation, add -3 times row 1 to row 3 and replace row 3 with that result. So how do I undo that? Well, do the same thing. So how do I get this thing back to the identity matrix? Well, multiply row 1 by +3 and then add it to row 3 and replace row 3 with that result. That +3 and the -3 will give us a 0 here, and that'll get us back to the identity matrix. So what is the inverse of this action? Instead of adding -3 times row 1 to row 3, I'm going to add 3 times row 1 to row 3. So this is the inverse of this matrix. If you multiply these two things together, you will get the identity. In fact, it would be a good exercise for you to go through and check that if you multiply these two things, you get the identity. If you multiply these two things, you get the identity. If you multiply this thing with itself, you also get the identity. Okay, here's a good example of how we might use elementary matrices, and we'll sort of tie all of this stuff into one nice theorem here for square matrices in a little bit. So we're given a matrix A, and we want to put this thing in row echelon form, not the reduced row echelon form, although you could do that. We just want to stop at the row echelon form, so just stop there. And when we do that, we want to keep track of our row operations, and every time we carry out a row operation, we're going to assign the corresponding elementary matrix to that thing. So what we're going to do is apply a row operation to A, apply another row operation to A, keep doing that until we get the thing to row echelon form. And we need to be able to do that in a finite number of steps. So we can always put a matrix in row echelon form or reduced row echelon form in a finite number of steps. And then again, order matters. So we'll see how to put this all together here in a bit. So here's our matrix A. How do we put this thing in row echelon form? So first thing we want to do is make sure that the leftmost non-zero element, we write that up at the top. So, and if it's a 1, even better. So I'm going to take row 2 and swap it with row 1 so that I get that nice leading entry. The leftmost leading entry is a 1 all the way at the top. So here's the row operation. We're going to replace or interchange row 1 and row 2, and here's the result. So from here to here, just interchange row 1 and row 2. Now, if you look at row 3, we can knock this down to size a little bit. All of these things are divisible by 2. So why don't we go ahead and clear out all of the 2's from row 3. So I'm going to replace row 3 with 1/2 of row 3. So here's my second row operation. I'm going to replace row 3 with 1/2 of row 3. So I get 1, -3, 1, 0. 1, -3, 1, 0. And so now what do I need to do? I need to clear out the leading 1 that's below this leading 1. So what do? I add negative row 1 to row 3 and replace row 3 with the result. Add negative row 1 to row 3 and replace row 3 with the result. So when I do that, negative 1 and 1 gives me 0. -3 is 3 plus -3 gives me 0. 0 and 1 gives me 1, and then -2 and 0, that'll give me -2. So you can see, now we've got this nice staircase. All of the leading entries move to the right as you descend, and then all of the zeros are at the bottom. All the leading entries are 1. So this thing is in row echelon form. And we kept track of our row operations like we normally should. And each one of these row operations, each one of these elementary row operations will correspond to an elementary matrix. So operation number 1 is swap row 1 with row 2. So here that is. We took the 3 by 3 because there's 3 rows. So we took a 3 by 3 identity matrix and swapped row 1 and row 2. So that's what we have here. That's our first elementary matrix E1. What was the second elementary operation? Well, I multiplied row 3 by 1/2. So that's what we're going to that's what we're going to have for our second elementary matrix. We're going to take the 3 by 3 identity matrix, multiply the third row by 1/2. So here is E2. And then what's the third row operation? Well, we took negative row 1, added it to row 3, and replaced row 3 with that result. So this is the thing we're going to do to the 3 by 3 identity matrix. Take row 1, negative row 1, and add it to row 3 and replace row 3 with that result. So remember, the identity matrix goes 0, 0, 1, and then if you multiply this thing by -1 and add it to this row, you get -1, 0, 1. So now here are the 3 elementary matrices, and remember, this thing, when you multiply A on the left by this, it will carry out that operation. And that's what we want to do. We want to interchange rows 1 and row 2 going from here to here. And then we want to take this matrix and multiply by 1/2. And then we want to take this matrix and add negative row 1 to row 3 and replace row 3 by the result. So those are the things that we're going to, those are the actions that we're going to apply to A. So start with the matrix A, apply this first elementary row operation to A. So that's why we write it on the left of A, and it is adjacent to A. So it comes first, right? And then what do? Second row operation corresponds with the second elementary matrix. So it goes here. And then we took the third operation, applied it to this new thing, and we finally got the the row echelon form of A is the product of these 3 elementary matrices, or we had to carry out 3 distinct row operations in order to get this. Carry out 3 distinct row operations on the matrix A. So start with A, apply operation number 1, take the new thing, and apply operation number 2 to the new thing, and then take the new thing and apply operation number 3 to it. And then you will wind up with the row echelon form for the matrix A. So make sure you're good on this process.